We have done first application of potentiometer, that is measurement of EMF of the cell. Today we will start the second application of potentiometer, that is comparison of EMF. Second application of potentiometer, that is comparison of EMF. So you have a cell. This is your potentiometer circuit. This is your driving cell. This is your external resistance capital R. This is your potentiometer wire E. The gradient of this potentiometer is K. K is potential gradient of the potentiometer, which is given. Gradient is given. It's potential. So if I connect this potentiometer through a cell of EMF E1 to a galvanometer G, the balancing length is L1. This is the balancing length, which is L1. So for the cell E1, balancing length is L1. So if L1 is balancing length for cell E1, what is balancing length? That we did in the last class. We have already done measurement of EMF using a potentiometer. So in that topic, we did what is balancing length. So L1 is balancing length for cell E1. So for your cell E1, balancing length is L1. So you can write your E1 as it's KL1. That's my first equation. The next what you can do, you can just detach this E1 from the galvanometer, take another cell of EMF E2, connect this E2 to the galvanometer, and the balancing length is L2 now. This L2 is the balancing length of the cell. So if I write this L2 as balancing length for cell E2, balancing length for cell E2. So E2 is its KL2. I can take the ratio of E1 and E2, divide 2 by 1. If I divide 2 by 1, then you can write this as E2 by E1 is KL2 by KL1. K will cancel this K and you are left with E2 by E1 is L2 by L1. So if you know the balancing length of the cell, then you can easily calculate the EMF of the cell. The EMF of the cell depends upon the balancing. So let's do a numerical on this concept. So basically cells are given in this manner. You have two cells, one of EMF E1, another of EMF E2, and they are connected in this way. It's not that straightforward. So you basically have series and parallel combination of cells. Series combination of cells. So okay, I will solve this numerical. See here, there is not, this 400 is not for a single cell. This is for the combination of cells. Now remember, if cells are connected in series in this way, then the equivalent EMF is E1 plus E2. But if cells are connected in this way, then the equivalent EMF is E1 minus E. Equivalent EMF is E1 minus E. This is the equivalent EMF if negative and positive are connected. This is equivalent EMF if negative and negative are. So Fatima, this 400 centimeter balancing length is for the case 1 or for the case 2?
E1 plus E2.
I said this E1 plus E2, not E1 minus E2. EMF of cell is proportional to balancing length. Greater the EMF, greater would be the balancing length. In which case EMF is more. You are right in your first attempt. In which case EMF is more.
E1 plus E2.
E1 plus E2. So the greater balancing length is for E1 plus E2. This is the logic. Is proportional to balancing length. So E1 plus E2 is K into 400. And E1 minus E2 is K into 200. You just have to calculate the ratio of this. So you can simply divide it. This is 1, this is 2. Okay, now do yourself. Just divide 1 and 2 and get the value of E1 by 2. I need E1 by 2. You can even, no, not, don't divide it. Don't divide it. You can easily, division would be complicated. Just solve equation 1 and 2. So we can add these two equations. This will cancel this thing. E1 plus E1 is 2E1. 400K or 200K is 600K. So your E1 comes out to be 300K. If I substitute the value of E1 in any of the equation, if I substitute 3 in 1, then E1 is 300K plus E2 is 400K. You will get that your E2 is 100K. And this is E1 300. If I take ratio of E1 and E2, E1 is 300K, E2 is 100K, the ratio comes out to be 3 bar. Then there's third and last application, measurement of internal resistance. So using potentiometer, you can also measure internal resistance of the cell. So while measuring internal resistance, I will use the concept of terminal potential difference. If you remember, we did a topic, terminal potential difference and internal resistance of the cell. So I will use some concepts of terminal potential difference. So let's start with a potentiometer. It's a potentiometer. This is driving cell of EMFE. External resistance is capital R. This is your potentiometer wire AB. If you remember, this was the circuit for measuring terminal potential difference. This is external resistance capital R. This is EMF of the cell. This is internal resistance R and this is K. The potential difference across the terminals of the cell was E if key is open. If key is open, then the potential difference across these terminals is equal to EMF. When the key is closed, then the terminal potential difference was E by R plus R into capital. This was the terminal potential difference when key was closed. This we did while doing internal resistance and terminal potential difference. I will use this concept here. So I'm connecting this whole circuit with the potentiometer. So this is the internal resistance. This is the EMF E. This is the external resistance R. And this is the galvanometer. So this key initially is open. And I connected this galvanometer to the system. So now this galvanometer will measure the terminal potential difference. This terminal potential difference. This terminal potential difference is equal to the EMF of the cell. If your circuit is key is open, this is key K. But if your key is closed, then it will measure the terminal potential difference, which is this. And don't confuse this R with R1. This R and R1 are different resistors. This R is connected with the potentiometer, while this R1 is the resistance of the external cell. So, when key K is open, if your key is open, that means potential difference across the terminals of the cell is equal to EMF. Then potential difference across this end of the galvanometer is E, and let's say balancing length is L1. Johanna, if balancing length is L1, so can you connect this E and L1? K is the gradient of the system. K is potential gradient. Johanna, if the key is open, then the potential difference across the terminals of the cell is equal to EMF. It should be KL1, right? If you have balancing length and you want to measure EMF, then this is always K times balancing length L1. This is equation number one. Clear, everyone? Padma?
Yes.
But when key is closed, now if I close this key, now Giovanna, tell me, the potential difference will be equal to EMF or it will be equal to terminal potential difference?
It will be equal to EMF.
Terminal potential difference is equal to EMF only if the key is open. But now your key is closed. So this is equal to EMF or terminal potential difference? Now we
Terminal potential difference.
Potential difference. So potential difference across terminals of cell is E by capital R1 plus small r, which is the internal resistance of the cell, into R1 is equal to, sorry, is this term. V, and this is your V. Now, when I close the key, the balancing length now shifts to some length L2. This is your balancing length. This is your balancing length. So L2 is, and I write this as L1 is balancing length in open circuit. This portion I'm using from the terminal potential difference and internal resistance of the circuit. So when I close the key, the balancing length is L2. L2 is balancing length in closed circuit. Okay, Jubena, can you connect this V and L2?
KL2.
V, which is equal to E by R plus R multiplied by R, this R1 is equal to KL2. That is equation number. Now you can simply divide one into. Divide one. If we divide 1 in 2, then you will get its E by R1 plus R into R1 divided by E is equal to KL2 by KL1. Gets cancelled out. This E will cancel this E. We are left with just R1 by R1 plus small r is L2 by L1. That's my equation. This is it. So I'm just taking reciprocal of the equation. R1 plus R by R1 is L1 over L2. So I can write this as R1 by R1 plus R by R1 is L1 over L2. So R over R1. So your R is, it's R1. It's L1 by L2 minus 1. So this is the internal resistance R, which is R1, L1 by L2 minus 1. This is how we can calculate internal resistance. If you have balancing length in open circuit and balancing length in closed circuit and this external resistance R1, then you can calculate the internal resistance of this. One last question of current electricity. Last question. This is on infinite series problem. So this is A, this is point B. This is 1 ohm. This is 1 ohm. This is 1 ohm. Okay, can you calculate the internal resistance of the cell, equivalent resistance of the system? All resistors are connected in series, so equivalent resistance would be 1 plus 1 plus 1, that's 3 ohm. But instead of 3 resistor, I keep on repeating this term. I'm repeating this term infinite times. So circuit will look like, so this is an infinite circuit. You have infinite resistors connected in series, and this pattern is repeating infinite times. So they're asking you to calculate equivalent resistance across it. So you're supposed to calculate equivalent resistance across the points A. The equivalent resistance. So to solve this circuit, you cannot use the usual methods of series and parallel combination because you don't have finite number of resistance. You can't add them up to infinity. To solve these type of circuit, there are certain tricks. The first step in the trick is to identify the repetition term. So this term is repeating almost infinite times. Not almost, exactly infinite. This term is repeating infinite times. Infinite times. Now, if I add one more repetition term, and let's assume let equivalent resistance of circuit the equivalent resistance of your circuit is R. This is the equivalent resistance of the circuit. So this is repeating infinite times. 1 ohm is repeating infinite times. The equivalent resistance of the circuit is R. If I add one more repetition term, if I add just one more term repetition term, what will happen to this R equivalent? On adding one more repetition term. It's like I'm saying add 1 to infinity. Will it affect infinity? Will the circuit change on adding one more term? No, right? Circuit will not change. Circuit will not change. The whole solution of this circuit is in this statement. If you understand this statement, then the rest is just mathematical calculation. Now, let us convert this particular statement into a mathematical equation. See what I said? I said on adding one more repetition term, circuit will not change. And I have written that equivalent resistance of the circuit is R. So we solve it like the equivalent resistance of the entire circuit is R. For the entire circuit, the equivalent resistance is R. This is the equivalent resistance of the entire circuit. Now I'm saying on adding one more repetition term, it will not change your circuit. So I'm adding just one more repetition term. And I'm saying that your circuit will not change. That means equivalent resistance will remain R as it. Okay, tell me, is it clear this point? I just converted this statement into a mathematical equation. This is the resistance of the entire circuit. I added just one more repetition term, and I'm saying on adding one more repetition term, your circuit will not change. Your resistance will remain R. Now, if I take equivalent resistance, like Afroza, how this 1 and R are connected? 1 and R, how are they connected? Series or in parallel?
Parallel.
Parallel. R and 1 are connected in parallel. If I calculate the parallel combination, this will be R into 1 by R plus 1. That's a parallel combination of R and 1. This one, this parallel combination of R and 1 and this one, all are connected in series. So you can write that your equivalent resistance is 1 plus this whole term, which is R by R plus 1, plus this one is equal to R. This will be a quadratic equation. Solve this quadratic equation and get the value. I'm making the quadratic equation. Is equal to R. 1 plus 1 will be 2. So that's 2 plus R by R plus 1 is equal to R. You can take R plus 1 as common. So that's twice of R plus 1 plus R is equal to R. Twice of R plus 1 plus R is equal to R. So you can multiply it here. So this will be, I don't have much space. Just solve this equation and get the value of R. There will be two roots of the equation. Solve this equation and get the value of R. Answers. No, Fatma, 1 ohm can't be the answer. No, not 1 ohm. 1 ohm is not a possibility. I'm waiting for the answers. Just make this quadratic equation and solve it. I will not solve this equation. It's simple quadratic equation. Yes, Jemina, this is the equation, but I will not solve it. Solve this equation and get the value of R. See, R square minus 2R minus 2 equal to 0. To solve this equation, you can use this concept. This is the quadratic equation of the form ax square plus bx plus c equal to 0. Have you done this thing? To solve this quadratic equation, you can use these terms. You can use that x is minus b plus minus root over b square minus 4ac over 2a. So your r is, instead of b, I'm using minus 2. So it's minus of minus 2. Have you done this relation in class 10?
Yes, sir.
So this is minus 2 square plus 4ac means 4 to 8 divided by 2a, that means 2. So r is 2 plus minus root over 12 by 2. So your r is 2 plus minus 2 root 3 by 2. So your r is 2. I can take 1 as common, 1 plus minus root 3 by 2. So this 2 will cancel this 2. Your r is 1 plus minus root 3. So r is either 1 plus root 3 or 1 minus root 3. So you have two roots. So r is 1 plus root 3 or 1 minus root 3. 1 minus root 3 is basically negative. Na? It's 1 plus 1.732, 1 minus 1.73. So it's 2.732 minus 0.732. Resistance can never be negative. So the actual answer is 2.73. Clear? So that was about current electricity. I just have left a color code of carbon resistor. Basically, this color code is not a part of syllabus this year. This is part of reduced syllabus. And this is not connected to any other topic. So I'm not discussing color code right now. I skipped this color